Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Simon Thorpe from the Business Review, and I'll be the moderator for today's session. It's our great pleasure to have VTT with us today, who will be discussing foam in papermaking, from a harm to an asset. Today's guest speakers are Erkki Helen, who's a research team leader within fiber product manufacturing technologies. We also have Harry Kaiskinen, who's the principal scientist within fiber product manufacturing technologies also. I'd like to take this opportunity to remind the audience that you could submit questions using the Q&A tool at the right-hand side of your screen, and you can do this at any point throughout the presentation. We're then going to allocate around 10 to 15 minutes to try and answer any questions or thoughts. So without further ado, please allow me to welcome the first speaker. Over to you, Erkki. Please click and carry on with your presentation.
Okay, thank you, Simon, and good afternoon and morning to everyone. So it's my pleasure now to tell you today about foam. That is something that we usually want to get rid of at the mills, and how you can actually turn that to your advantage. However, before going to tell you about the foam forming itself, let me just briefly introduce what is VTT, the Technological Research Center of Finland, all about. So basically, we are, as the name says, we are a research center, and what we are only doing is research to help the companies to develop their business. So we are about 3,000 researchers working at VTT, and our turnover is around 300 million euros. So we are a multi-technological research organization, which basically means that we are working on all the fields of industry, coming from the construction to mining, ICT, medical research, and today we are mostly concentrating on the fiber-based industries, on the forest sector. And our aim or the slot here where we are operating can be seen in this image. On the lower right-hand side corner here. So basically, if the industry is doing their product and process development and the business, universities are doing the basic research. So VTT is there in between to helping to take the research into the advantage of the companies. And one fact of VTT is that we have extensive and unique research and testing infrastructure, something you will see some examples also today. Then let's go to the next slide. So what I will tell you with my colleague Harry Kaiskinen today is that how this foam forming actually increases the competitiveness of the current products that the companies are making, especially through increasing the resource efficiency and making lighter weight products. You will also hear about how we turn our existing paper machine pilot line to a foam line to get the feeling on how that could be done in practice, and also at the end you will see some demonstrations on new business opportunities outside of the paper and board industry. So, starting the foam forming. Before going to the foam forming, I would like to share you one slide about how this all started. So basically in 2008, the major Finnish paper-making companies, board-making companies, machine manufacturers and chemical suppliers together put up a research agenda that how we should look at the future and set as a goals that we should aim at radical resource savings, namely meaning savings in the fibers, raw materials, energy and water. And not that being enough, we should think about ways to renew the industry and find new fiber-based products outside of the traditional value chain. And as a starting point, we took that we have wood, we have a lot of emerging industrial biomaterials, and also nanomaterials. And we here started this research around microfibrillated celluloses. And what was lacking was actually the technology how to make this. And after about 1 or 2 years research, it became evident that actually the foam forming technology is the most promising technology to achieve these goals. And we also found out that it's not only something that is suitable for packaging, paper and tissue industry, but also it has something to offer for the non-wovens, insulation materials, composites, and so on and so forth. And what is then the foam forming? The foam forming is such that typically when you are making board or paper, you mix your fibers with water. Here you add a surfactant which enables you to inject air into the furnace. So basically you have fibers, water, and air. So that the typical air content is around 30 to 70%. And basically what this foam does, or these bubbles do, is that they prevent fibers moving when you are forming the network, and more technically said that they prevent the flocculation in the head forms. Here you have two images of the foam. Like here on the left-hand side, it's like dishwashing foam. That is something that you want to avoid, but you have to have a certain kind of foam where the bubble size is around 100 to 200 microns, and it goes around the fibers in the suspension. And just to exemplify this, I would like to show you a short video which basically explains that what is taking place. So here you see in our pilot environment, this is the head box. The foam is coming here. This is special head box now to see the foam better. So it's coming here. Then you are sucking the foam away, and basically you are left with a structure that reminds the ordinary pork, but it doesn't. It does have So I just play this quickly again. So you see that the foam is used as a transfer media in this region, and the product is more or less similar than it's nowadays. So I would like to tell you something, that what is the value for this first to pork and paper. So why to mix fibers with foam? There are several benefits. First, you get excellent formation. So basically your structures are uniform, which you can use either to improve the quality of your product. You can start to utilize longer fibers or less refined fibers because you don't have any problems with the fiber flocculation. And it also improves the moldability or formability of your product. Other advantage is high bulk. So basically, you can increase the thickness of your structure, lower the density, and when properly reinforced, then you get lighter board or paper. The foam also improves dewatering, which you can take either as a drying energy savings, or then if you are using lower wet pressing pressures, you can again increase the thickness of your product. Last but not least, the foam enables you to utilize a wide range of raw materials, from nano materials to long fibers, and also it creates you possibility to create structures and products with unique properties which you can then utilize in your marketing and sales. So I will next show you a couple of examples on how this helps. Here is one example on the formation. So on the right hand side you can see that ordinary water late sheet, the unevenness of it, and then taken to same furnace, what is the evenness in that when you are using the foam technology. And on the left hand side you can see that this formation number here, so basically the unevenness is greater in this area. And here you have three different kind of fibers, spruce, CTMP, pine, and birch. And these blue bars here denote what you get, what kind of result you get with the ordinary water late technology. So the longer the fibers, the spruce CTMP fibers are the longest ones, the poorer the formation. Then when you turn to the foam forming, you can see that actually the formation is in all cases better than with the water late technology, and it's also independent of the fiber length. This you can use as an advantage so that you can either increase the forming consistency in your machine, and then it leads to higher strength and moldability. And the next slide here shows the strength. This is now more for the lightweight products when the basis weights are below 80 grams. So here you can see the tensile index. So it's basically the tensile strength divided by the basis weight. So these blue diamonds here represent that with the water late technology at low basis weight, the tensile index starts to decrease because you have uneven structure and you have weak points in your paper. Whereas in the foam technology, the tensile index remains more or less constant to the low premises. So basically here you can see that there is a huge increase in the tensile index at low basis weight. Another example here is that if you have or when we have a uniform structure created by the foam technology, you can also increase the stretchability of the board. So here we have actually made foam for substrates which we have impregnated with polymers to make it thermoformable. And at the currently we are around the level of 2 centimeters, but we are constantly improving this, and we are aiming to replace plastics packages in grease-strong tubes. Then the next slide shows how we can significantly reduce the fiber in the board manufacturing. So here in this image we have the bulk, which is the inverse of the density in this axis. So the low density structures are here, and this axis here describes the thickness directional strength of the board. So basically we would like to be in this region where we have low density but high strength. With the current technology, however, our operating window is around this green area here. So if we refine the fibers more, we get more strength, but also the structures are more dense. What the foam forming enables us to do is actually increase the bulk, basically create low density structures. However, the strength itself is not great, but that we can help so that we take an advantage of raw materials here, the cellulose microfibers. When we combine foam forming together with the cellulose microfibers, we can strengthen the web such that actually we can create 54% lighter sheets which have the same properties, namely the modified Scott bond, the Z directional strength, the bending stiffness, and the compression strength. So this is like a big result achieved in the laboratory scale, which actually led us to the decision that we want to go and upscale this technology. And now I will next show some results from our pilots. Just first the implication of this in the research efficiency from the cost point of view. On the right-hand image, you can see that with the current technology, the variable costs, they mostly consist of the fiber costs. Then we have energy, chemical and raw material, water costs. But if we can reduce the amount of fibers, here is the literature reference when we started this, and this is the lab scale result I just showed you. There are tens of percentages saving potential with the foam forming technology. And even if we won't reach this at the final mill scale, I think that reaching something like 15 to 20% savings in the variable costs has a huge impact on this industry. So the most of the savings will come through the reduced fiber amount, but also the drying energy reduction through the decreased basis weight, and improved dewatering is significant, and also the chemical consumption is expected to decrease as we have less raw materials. So now to the pilot scale results. So here is one example of the dewatering improvement. So on this axis, we have the foam density. So basically when it's 1000, it means that we have ordinary water late technology. The press dryness here means the dryness levels after the press section, which in this case was about 39%. And when we turn to foam, there is a huge improvement in the dryness after the press section, about 5%. And 1% unit usually means 4% savings in the drying energy. So this result implies that there might be something like 20% drying energy savings, which could be reached by turning to the foam technology. The next slide just shows the formation improvement in the pilot scale. Here is the water late and the foam late, and these are the different structures for the foam and water. But basically this just shows that the result that we were able to reach in the lab scale is also achievable in our pilot. And the last example from the pilot scale exemplifies the strength improvement due to improved formation. So here we had a mill furnace and on our machine at 40 grams per square meter paper. Here is the commercial mill reference paper made with the water late technology, and the tensile index for in the machine direction and in the cross direction stays about the same at the same level for foam densities above 500 in this case, whereas the bulk is almost double. So this just shows that this technology has a clear strength improvement potential at low basis weights. So coming back to these benefits, there is the formation, high bulk, improved dewatering, and utilization of different raw material compositions. And the benefits are, as described there, is the resource savings in the raw materials, lightweighting of your products, improved dewatering leading to drying energy savings, and then also utilizing this technology to manufacture products with unique product properties. But at this stage, I would like to ask my colleague Harri Kiiskinen to tell you something about how this technology was upscaled from the laboratory scale to pilot. So please, Harri.
Hey, thank you, Erkki. Good morning, good afternoon. This is Harri Kiiskinen speaking. So I will tell you very briefly how this modification was done in our pilot. And before going to these details of the foam, so I will tell what kind of pilot we currently have. So basically it is a small paper machine, having a speed and the roll dimensions pretty identical to production units, but the width of the web is very narrow. So it's only 300 millimeters, which means that we can really, with this device, run full speed experiments using very low amount of raw material. We are speaking in kilograms, 50 kilos or less. Of course, if there is a need to make raw samples, then more raw material is needed. The forming section is the first part of the unit, and there we have different options. It could be a gap former, a hybrid former, or a full linear. And this forming section of that pilot was built a little bit more than 10 years ago. The press section consists of a single nib extended nib press, which was built 2007, so it's quite new technology. Then this automation system is MetsoDNA platform, so it is operated through that. We have a data acquisition sulfur wedge, which collects more than 600 channels from the device. And then there is a sampling unit, and we will make reels at the press dryness, and there is an offline dryer. So then this modification to the unit to a foam forming research info. So the first thing is really generation of the foam, how that is made. And then, of course, we need to know what kind of foam there is in the system. There are certain needs for online measurements. We need to move from foam from one place to another, foam pumping. And then for head box, there are several options. And then the vacuum system, how to run that, and basically this running concepts, how to start up the machine, how to shut down the machine, and this kind of questions, how to move from foam to water forming and vice versa. From the image you can see the operator running the system from the control room through this DNA system. Okay, then the first part was this foam generation. We have actually two different options for that. The first one is tank mixing, which is basically a huge kitchen mixer. You put your pulp suspension and surfactant in a tank, and then some kind of mixture, very intensive mixing, and it generates the foam. It's very robust, good technology. It's used today in some nonwovens production, and typically foam made using that technology, it is quite stable. So this half-life time, which is one measure of foam quality, is more than 3 minutes. Another technology we are using, it is something we call online generation. So basically from the figures you can see that there is an approach system, and few meters before the before the head box there is a generator modules in where the air is injected and the surfactant is added in a pipeline just before the generator unit. So by doing the foam in line before the head box, we can actually do a very different kind of foams, very stable or very unstable foams. And we also can save some surfactant, and we have a wider window for controlling the foam properties. And in practice, actually, we have both of these systems there, so it could be some kind of mixture of these two technologies. The foam could be generated in the tank, but the fine-tuning could be done just before the head box. And then some changes we did for the machinery. First thing was pumping. So we are using centrifugal pumps in our system, and you can pump foam using that kind of device. But at certain flow rates, there is the risk that air accumulates in the impeller, and then the flow rate through a pump decreases. And so there is a need for a special type of pump having air removal in there, and that kind of pumps are commercially available. Then for head box, so two options. Erkki showed a video from that the closed configuration. That is one way of doing the forming. But what we have learned quite recently that you can as well use the open jet geometry. In other words, the same head box you are using today in paper or board making. And there is a short video from that open jet, so you can see the free jet coming out from the head box. In this video, the running speed is somewhere around 500 meters per minute, and then the forming section is in hybrid mode. So the foam goes through the fabric, and then there is this upper wire unit, which kind of makes the structure more uniform through the thickness. Okay. And then the one more thing was this vacuum system. So as mentioned earlier, so this density of the foam is quite different compared to water. It varies typically between 300 and 800 kilos per cubic meter. So all these vacuum system levels, which are typical in traditional forming, they needed to be changed. All these suction heads and those, basically this vacuum system capacity has to be adjusted for foam. But same machinery works foam as well if the capacity is high enough. And then this online measurements. So this foam density is kind of for basic measurements. We need to know how much air there is in the process and what type or what kind of density we want to run. Foam is also there is some air, so it is compressible. So when we do some measurements at certain point, the pressure is changing in the pipelines. For example, the velocity, flow velocity is changing in the pipe. So you need to know where the measurement was done at which pressure in order to be able to calculate, for example, a jet speed out of those. Foam stability is another. There is this upper image showing device we have built. So basically it takes a sample from a head box and using some machine vision devices, it sees how fast the water drains out of the foam, which is the measurement for this foam stability. We can also measure the bubble size distribution if needed. So this bubble size and controlling the bubble size is one way of controlling the pore size distribution in the paper, and that is something we currently don't have in line in the process. We do those measurements in the lab at the moment. So as a short summary of this modification we started in early 2012, and less than a year we had this foam forming process ongoing. And so far the maximum speed has been 900 meters per minute. Basis weight range we can study is from 30 to 200 grams per square meter. We will get press dry rolls out of the system, can dry them, and typically the roll length, of course, depending on the basis weight, it is typically between 500 meters and 1 kilometer. We have two generation technologies. The system is instrumented for foam, and as I said earlier, you can use the same machinery, same components, and run the trials with water and with foam even during the same day. So there is no need to remove anything when you move from one technology to another. And there is a third video here showing how this system really looks like. And there is you can see from the video there is roll coming out from the system, and this is you can see some fabrics. The forming section is back there, and the press section is on the right hand side, and that is the roll coming out from the pilot. And then one more slide. I collected our partners who have been involved in this piloting of this technology. And that's about it. I was planning to tell about this piloting, and then Erkki will tell more about some future applications of this technology. Please, Erkki.
Okay, thank you, Harri. So I will continue here by a couple of examples how to expand the use of natural fibers. So first of all, what this foam actually does, it enables us to combine raw materials in a way that we haven't been able to do before. So naturally, we have the natural fibers, we can combine them with nanomaterials, but this also gives us a possibility to utilize natural fibers together with synthetic fibers or regenerative fibers, and as the foam itself stabilizes the suspension, we can start also to use very lightweight materials, lighter than water, together with foam, and naturally put there also some functional chemicals which then help to achieve the properties for the products which we want. And next I have here a couple of examples. First, what would be the value for the nonwovens? So first of all, we can start to incorporate bio-based fibers to the nonwoven sheets. That's one advantage. Other one is the formation improvement for the long fibers. The image here on the left-hand side shows some other technology where we basically take recycled fibers and turn them into the viscose-like fibers, which can then be used as a bio-based materials in the manufacturing of nonwovens. From the technological point of view, if we compare the currently used dry lathe technology to the foam lathe technology, there is a big potential in increasing the machine speed and therefore increasing the production capacity in the production of nonwovens. On the other hand, if we go to the wet lathe technologies, they use at the moment extensive amounts of water in the wet end as the fibers are longer than in the ordinary paper making. So there is a potential to increase the consistency of the forming and reduce the pumping energy in the wet end of the nonwoven wet lathe machine. Another example from another area which extends to construction insulation and some special packaging materials is shown here. And if you now remember the packaging board figures from the beginning, where our bulk levels were around up to, let's say, 6 to 7 and even 8. Here we have manufactured samples whose density is from the level of from 8 to 26. So basically the bulk levels are from around 40 to even 120. So if we compare these to the ordinary styrofoam, expanded polystyrene, we are at the same level in the density here, what we can make from ordinary paper making raw materials like heavy thermomechanical pulp fibers, pine pulp, or then mix them with, for example, PCC, precipitated calcium carbonate. And the first results show that actually thermal insulation capacity of these structures is at the same level than the commercial mineral and rock wool insulation materials at the moment. Just showing another example at reaching extremely low density structures with the foam. Another interesting property for these low density structures is that actually we tested not only the thermal insulation but also the sound absorption capacity. And to a positive surprise, this image shows here that what is basically the weight per cubic meter of these materials, and here is the sound absorption coefficient at 500 hertz. This is actually one of the most demanding frequencies to attenuate, for example, in car manufacturing. And these blue dots here present the commercial products that you can buy from a shop at the moment, and the first test already showed that the sound absorbance of these products made from natural wood fibers is around the same level without any optimization of the structure yet. And the final example comes then even further away, where we have utilized this foam technology to manufacture high-performance growth media for plant production. So at the moment, most of the plants are originally, they are the seeds, the substrates are either based on rock wool. Then there are also plastic pots which are filled either with peat, or then you can use peat in a polystyrene foams. So what we have done here is actually that we have been forming these substrates from moss, so that actually you don't need any like synthetic materials, so you don't need any pot here. So basically you can form the moss substrates where you can put the seeds, and actually the experiments in gas houses have shown that these are actually very good substrates also from the production point of view, so the plants like to grow in a moss. This is one example like from another market. So now I would like to conclude the whole presentation. So we have three parts. So the value for board and paper, upscaling, and then these future applications. So if you look at the key learnings from this session, I would say that first, we think the benefits for packaging board, different kind of paper grades. We have seen that foam can be used as it improves the formation, creates even structures. You can use it to create lower density structures. It improves the dewatering at your machine, and you can start to combine raw materials in a way that has been impossible in some cases this far. I would say that one of the nice surprises for us was that when we started to upscaling, it took less than a year to scale up the process so that we could use it at our pilot scale. About a couple of months more than 1 year when we started, we made the first reels, and about 2 years we have already reached 900 meters per minute running speed. And I think that as Harry showed here, one of the benefits is that it seems that this technology is very well suitable for the current infrastructure at the mills. So basically at the moment we are running our trials so that we can run during the same day with the same equipment, both water trials and foam sheets or reels. So we believe that this is a very versatile technology to be used in the future, so that we can also start to use natural fibers in other applications. If we then take a look at the value of this, so we believe that this is a next generation manufacturing platform for fiber-based products. So this can lead to lightweight packaging materials, lightweight board, paper, and also tissue products. It can bring us significant energy savings, and it gives companies ways to differentiate from their competitors by creating products that have unique properties. You can start utilize raw materials in a different way and think about what would be the most beneficial places utilizing your current infrastructure to adapt this technology with relatively low investment costs. And this agile adaptation here actually means that it seems that with this technology, it's much easier to utilize the same machinery to produce products which have a much wider product property window that the current machines have. So basically now, if you have a machine, it's usually built for making one product. It makes that product for tens of years, and it's very demanding to change the existing infra to make some other product that it nowadays does. We believe that this technology actually is much more agile, so that when this is taken into use, to adapt to the market needs that comes in the future. And we believe that there are business for both large international companies as well as small and medium-sized enterprises. And why we believe in this technology is that we already know that this is commercially used for specific nonwovens, and what we aim at is to take the benefits of this technology and transfer them to the board and papermaking industry. With these words, I would like to thank you for your attention and let Simon take the lead from this on to ask you one question. Thank you very much for your attention.
Thank you.
Brilliant. Thanks, Erkki. Erkki, just move your slides forward a couple back to the poll question so it's on the screen there. Brilliant. Okay, so ladies and gentlemen of the audience, we're now going to run a poll. As you can see on the right-hand side of the screen, a box has appeared. If you would like to just sort of read through the question and select the answer that's relevant to yourself. So the question is, what would be the most relevant driver for you when introducing foam forming into your business? So we've got multiple choice answers here. So it's energy savings, utilization of longer or less refined fibers, differentiation from competitors, reduced raw material usage, manufacturing of new products, or the increase of production speed. Guys, just while we're giving the audience a chance to sort of review and select the right one, and please to the audience, once you have clicked it, if you just press submit as well, that will give us the answers. So Erkki and Harry, just while the audience are doing this, can you just give us your ideas on what you're trying to find out from this poll question?
Yes, sure. So what we are trying to find out that we have been discussing, and we have been approached quite a few companies recently regarding this foam technology, and it seems that there are different interests in different companies, why they would like to adapt this technology and why they are looking after this. So we just want to know that regarding this audience here, that how do they see this and what would be the most beneficial for their business in order to be able to also think about the next steps in the research to be able to answer those needs. Perfect.
Okay, so we've the poll is closed off now. So what we're going to do, we're actually going to publish the results, and they should come up on the right-hand side. So as you can see, it's come up as D being the most popular, 41%. Basically, reduced raw material usage. Do you want to just talk about the results and is it what you imagined?
Yes, sir. Actually, I was expecting that this reduced raw material usage will be the top one, but I'm happy to see also that there is also other needs like this manufacturing of new products, for example, utilizing the existing infra, differentiation from competitors. So I think that this is a very valuable information for us. So thank you for answering.
Great. Okay. So, I mean, I'll hand back to you guys then. If you want to just conclude the rest of your slides, and then we'll move on to the Q&A. Well, I've seen we've got some great questions in. So, yeah, I know you've got a couple more slides, and then we'll get onto that.
Okay. Thank you. So just to summarize, so this has been one opportunity. We have now here some 10 to 15 minutes to discuss, or not to discuss, but answer your questions. But if you want to have more information, please just contact us. Here are just a couple of examples where you can read us, the PaperCon to be held at the end of this month, then the pulp paper trade fair here in Helsinki, and then also the PTS Paper and Board Symposium in September in Munich if you want to discuss more with us. You are naturally welcome to contact us whenever, and we would like to also invite you to the foam forming excursion to Jyväskylä. So basically this will be taking place in connection with the pulp paper trade fair in early June. So basically you would have the possibility to see our foam forming demonstration samples, see our pilots running, and also at the same time to be able to visit Valmet and see their latest advantages in the paper and board making business. So with these words, I would just like to end this, and there are also my contact information if you are interested in knowing more. So please just contact me, and we can discuss more. And you are always welcome to see our facilities as well as feel the product samples we have been making this far. Thank you.
Right, thank you very much. Okay, so if we move on to the Q&A session now, we've got around 15 minutes, so we'll try and get through as many questions as we can. Please do continue to submit those. If we don't, unfortunately, have a chance to get back to yourself, I'm sure the guys over at VTT will get back to you as soon as they can and address your question. Okay, so Erkki and Harry, first question for today. What has been the biggest surprise when dealing with foam forming?
Biggest surprise. I think that if I answer first, so I think that actually the biggest surprise for me as a researcher has been how fluently this has gone, this research, because usually when you start something new, some new research, you encounter a lot of problems and everything takes at least 3 times as much time as you have in original thinking. And I think that here we have been in some cases even been able to go on faster than we thought. So I think that that has been the biggest surprise, that there hasn't been very, like, so to say, bottleneck which would have stopped us, and we are now already running pilot scale trials. So I think that has been the biggest surprise from my point of view.
Okay, on to the next. So, how is foam density maintained throughout the furnish? And it goes on to say, do the bubbles not join together?
Well, that's a very good question, and it really needs a very intensive mixing or intensive generation. So as I told earlier, we have 2 possibilities for that, and then if the foam is quite stable, then these air bubbles, they really block the fiber movement, and it is very uniform fluid, and there is it's quite uniform throughout the structure. But then the interesting thing is that this online generation, we've been thinking a lot how to make such a foam which you generate it in a head box and it disappears in after a few meters, because basically in order to make a good formation there is no need to have that kind of stable form, and there this uniformity comes more critical, and if there is a very small amount of surfactant, then the bubbles, they do join together and form a bigger bubbles, and then that comes critical. But it really comes to this amount of surfactant, type of surfactant, and right type of mixing intensity which is needed.
Okay, thanks. Can the size of equipment, so we've got pumps, pipes, tanks, etc., be reduced due to the compressibility of air stroke foam?
Well, when you think a pulp suspension having at a certain consistency, which let's start from the same consistency as it is in a paper machine. When you introduce this air, the volume increases. So it, for example, doubles. But then if you can, and because of this nature of foam and this recirculation blocking effect, you can actually increase the consistency as well. So you can, if you double your consistency and you then introduce 50% of air, you are in the same volume again. So basically, it compresses in the pump and in the pipelines. That could be slightly smaller equipment, but then we are speaking roughly the same size of machinery, which means that if there is an existing machine, it could be used for this technology, relatively same speeds and same production rates.
Okay, thank you. So the next question that's come in is, how is paperboard stiffness impacted in foamed board?
So if you think about the paperboard stiffness, so basically that comes mainly from the thickness of the board. So if you create like thicker structure using the foam, then you also increase the stiffness. So basically the thickness is the main attribute to create the stiffness, to be short.
Okay, thanks for that. And then what are the limitations on fibre length and the amount in the fibre formulation?
So I think that is something that we do not know yet precisely, that what will be the limitation. The longest fibers that we have run at this moment, I think, is around 10 to 20 millimeters. So much longer than we usually use in paper or board manufacturing. So we are there at the moment in the non-woven side, but to be honest, we don't know the limit, and we are just looking at and stretching it.
But for wood fibers, normally this fiber length and formation, they are kind of coupled. But using this technology, as was shown in one of these Erkki's figures, the formation is pretty uniform, and it's not a function of fiber length. You can make a very uniform structure from 2 millimeter wood fibers.
Brilliant, thanks guys. Okay, so the next question here is there a significant variation between cross and machine direction tensile strength?
That's something we can really control, similarly as in water forming, so this orientation could be controlled, and using this technology we can actually make a very highly oriented structures having a tensile ratio much higher than in normal water-laid paper making. And on the other hand, this ratio could be quite small as well.
Okay. Now, I know you touched on this on a previous question, but just to follow up, it says, is there foam actually entrapped within the sheet? And if so, what is in the bubbles?
No, actually the foam is just a transfer media, so there will be no foam left in the final product. So the bubbles will be like taken away from the structure.
Yeah, that's true. If we go in a very detailed level of that question, so that is something we can really control, and there is an article coming out very shortly in where we studied a different type of foams, meaning a different bubble size, and how this bubble size was inherited to a pore size distribution of a paper. And that is something, well, for certain grades, for example, there is a need to control your pore size distribution without, for example, refining the fibers. So this could be an option for that.
Okay. So it says you showed that in terms of bulk strength compromise, the interest of foam forming is mainly for low grammage, in brackets tissue. Does it mean that for higher grammage it is not interesting? And then it goes on to say, or only with MFC?
So certainly not so. I mean, it's also applicable to high grammages. But I mean, if you want to get the benefit from the foam only, then you get the benefit for low grammages, I mean, due to the formation improvement. If you want to like reduce the raw material at high basis weights, then you can increase the bulk with the foam, but then as there are less bonds between the fibers, you have to strengthen those bonds and add some strength additive to the structure. So basically, you can do it both for low grammages and high grammages, but how you make it in practice will be different.
And also for multiply products, when we can make a very uniform structures, it means that you can make a thinner surface layer, for example. If the middle ply, for example, if the formation there is improved, then there is a big potential of saving fibers, also this more expensive top plies. And this stratification or multiply structures, that is something we have been during this year building some facilities. We don't have that much results yet, but later this year there is a possibility to run that kind of multiply products as well.
Perfect, thank you. Obviously, I'm conscious of time, and I've noticed we've got quite a lot of questions, but so we're not going to have time to run through them all. But to the audience, please do keep submitting, and I'm sure the guys at VTT will get back to you in the coming days. But there's a question here that I don't know if you can answer it without knowing the full sort of scope of the project. But it actually says, what is a typical investment cost for adopting this technology?
Yeah, I think that the investment cost actually depends on the machine size what you have. But I would say that it's like from 5 to 10 million euros for a typical like packaging board machine. So it's not a drastic cost, but I mean that's like just an estimate here. But I mean it generally depends on the machine. But I would say that as far as we have noticed, we haven't been making very big changes to our pilot environment, and I would expect the same to be true also in the mill scale. But I mean that remains to be seen. Although we have got, I would say, great results here, we are in the beginning. There are still like issues to be solved together with companies and really before we can take this into commercial or industrial use.
Okay. Next question is, have you tried injecting different gases to create the foam?
I think that's different than air. At the moment, no.
At the moment, in this scale, no.
No. So we have been utilizing the simplest approach here.
Okay, thank you. How fast have you been able to run with the higher grammages? And it says 200 gram brackets. Is the 900 min just at the lowest weights?
This 900 was run at the, let's say, kind of printing grade grammage somewhere around 60 to 70. So I would say that the 200 at the moment with this dewatering capacity we have, it is somewhere around 300 to 400 meters per minute. but it is just a question of those devices we have there at our pilot. But technically, it would be possible to run higher grammages with the higher speeds. And something we are going to do later this year, so we will try how this gap forming technology works, so that will also increase the dewatering in our case. So we will see later this year what would be the maximum speed with higher grammages.
Then I would say that actually this increasing the speed hasn't been our primary aim. So in the upscaling we have been like concentrating on running stable trials over hours in our environment, and this speed has been like the second or third priority in our trials.
Okay, guys, just looking at the time, I think we've got time for one more question. Hopefully the audience can stay with us. I see that there's lots of you still out there. Okay, so what is the reason that drying energy is lower after pressing? Wouldn't the higher bulk reduce efficiency?
Good questions and many things there. The higher bulk, of course, it reduces the contact heat transfer in the drying, but we will see that it comes mainly due to the lower surface tension of water, so it comes out easily. Also, we have studied this pore size district or structure of a paper, and it is slightly different than photolate, and also some rewetting issues might happen differently in the case of foam forming. But that is something we are also looking more carefully at the moment.
Okay, perfect. Right, what I wanted to do is just give yourselves, whether it be Erkki or Harry, just a couple of seconds just to sort of summarize, and then what we'll do is we'll wrap up the session. But yeah, I mean, over to you if you just want to sort of address the audience for one final time today.
Okay, thanks. So first of all, I would like to once more thank everyone for attending this, and also remind you or tell you that you each should have got the feedback questionnaire. So if you have something that you want to ask from us, please just use that one or contact us directly. We are willing to discuss with you more and think about that how this technology could be helped in your business. So from my point of view, thank you very much.
Okay, thank you so much.
Thank you, Erkki and Harry, for what was a really great and interesting presentation, and obviously thank you to VTT for sponsoring this session. The presentation slides and the webinar recording will be available at www.business-review-webinars.com in the coming days. And we look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and you can follow us on Twitter @BRWebinars for daily updates. And you can also join our LinkedIn group, Business Review Webinars, to join discussions. So thank you all once again, and I hope you all have a nice day.
Okay, thank you.
Bye-bye.